My name is John Wild. I'm here with Darren Lynch, and I'd like to welcome you to our webinar today on optimizing water turbines with the use of CFD in SimScale. Just to briefly introduce myself, and then Darren here is also going to do the same. So I'm the Application Engineering Director here. I have, I guess, a few years now of experience with CFD through various different industries, applications, and companies. I'm pretty used to managing teams, and now I'm managing the pre-sales and post-sales teams at the SimScale Munich office.
Hiya, and my name is Darren Lynch, and I'm experienced in CFD and engineering design. I studied aerospace engineering at Brunel University, and I'm now part of the application engineering team here at SimScale.
Okay, so briefly just to cover the agenda for today, we'll probably talk, I guess, for 20 to 40 minutes or so, depending on how many questions we have. And please feel free to ask those in the chat, and we'll either talk about them as we go or possibly at the end. It depends on what's asked and how it kind of fits into the discussion. So initially what I want to cover, and pretty quickly I would say, are the benefits of using simulation, and then run through an introduction to SimScale. So if you're not familiar with who we are and what we do, we can cover that in the first couple of topics. And then we'll dig into water turbines. I found through doing some research I'm actually quite interested in these, so I'm going to show a little bit of history about them too, and then we'll kind of dig into a specific type of turbine, how to analyze it in SimScale, and then how to optimize it as well. In the middle of that, we'll kind of give a live demonstration, and then we'll dig into some results as well. So how can we actually figure out what's happening inside the turbine, what kind of pressure drops we're seeing, that kind of stuff. And then at the very end, we can cover any questions and answers or answer any questions that have been asked as we've been going. Okay, so initially, just to talk about the benefits of simulation, and really I mean, there's many, but I'm going to try and talk about these with water turbines in mind. So obviously, these turbines can be enormous, and we have a few photos in a little bit that we'll show. But thinking about reducing time investment and minimizing failures and reducing costs and reducing physical prototyping, a lot of those things kind of come together. So most of these can't be prototyped. I mean, they're enormous. And I guess I would say they're kind of optimized from one design to the next and one installation to the next. But what if you could, optimize them before they were built and make sure that you really had the best possible design before any manufacturing began? And that's going to save a lot of time, it's going to save a lot of cost, and at the end it's going to produce a better product than it would have otherwise. And I think the other point as well is minimizing failure. So the flow can move pretty fast through these things, and if we can avoid and hopefully, or minimize and hopefully avoid cavitation, we're going to reduce erosion, and we're going to increase the lifespan that the turbine would survive for. So again, just through using CFD, and I say it does a lot, right, behind the scenes. It's easy to use, but there's a very huge kind of calculations going on behind, so we can predict and give you an idea of where fluid might cavitate, and then we can reduce failures and improve the lifespan of the model. Just a quick introduction to SimScale as well, to talk about who we are. We're a cloud-based and browser-based simulation platform. We have CFD and FEA capabilities. I think we're really built to free engineers and designers and architects from the constraints of requiring local processing power. I'm just running a small laptop to what you can see here, and it does everything that I need, and everything is done remotely and on the cloud. And I think this is probably the last slide, and then we'll kind of dig into things specifically talking about the water turbine. But there's a lot here I think that we should talk about. So all in one basically is that we have CFD and FEA together, right? So if you do start collaborating with us and working with us and utilizing SimScale, you have access to everything at once. So you can use CFD and FEA together. We have real-time support, which is one of the reasons I joined the company, actually. I love the idea. And we have support in product, so you can chat with us anytime. Of course, you can email us, call us, whatever suits you best. But I think the live aspect and the immediacy is a huge plus for us. You can also collaborate amongst yourselves, so you can share models just with URLs, and that means you can collaborate across the world in seconds, and you can also collaborate with us. So within any project, there's a share with support button. If you press that, we can then see your model, and we can begin to help you straight away. I'd say cost efficient is an understatement. It's free, right, at the beginning, so you can basically start using SimScale now. You can sign up for a community account, and there's no charge. Everything you do is public, so other people can see, but you can start to experiment and get an idea of what we can do and how we can help you with no cost. Okay, so let's dig into today's topic. We're going to talk about water turbines and how to optimize them. But I wanted to show this photo for a couple of reasons. One is that these things can be enormous. This is capable of producing 150,000 horsepower, which sounds like a lot. I mean, I'm into cars, so that's way higher than anything I've ever heard of, and it's enormous. And the other interesting fact for me was this was taken 3 years after my dad was born. So my dad was 3 when this was taken, and we've been engineering these massive structures for that long, and my dad's pretty old. So to me, that's interesting. And they've been around for a long time. So obviously, they've been around for longer, about 135 years in total. But I thought it was an interesting starting point. And this is also the type of turbine that we've analyzed and that we're going to talk about in about 5 minutes. Before we do, I thought it is interesting to share, and this is something that I'm passionate about, moving away from fossil fuels and utilizing more renewable and green sources of energy. I mean, hydropower essentially can be free energy, right? I mean, the water flows from mountains and all the time, and we're not always utilizing it. At the moment, we're utilizing, or it's providing us, as you can see here in blue, about 16% of the world's total energy. We know that we can do better, and we know that even through optimizing the designs that we have, we could do better. And that's kind of where I think I would like to help, and hopefully SimScale can too. So throughout the years, there's been multiple different iterations of turbines. The first one was produced in 1827, and interestingly for me, I couldn't find a photograph, but I'm going to go and get one. So it's actually in the Deutsches Museum here in Munich. I've been there many times. Sometimes it's interesting, sometimes it's not, but I think now actually I have a reason to go, and I'm going to go and find this turbine there and take a photograph. After that, the Francis turbine was produced in 1849, and the interesting thing about that was there's been other things designed afterwards, but actually this is the design that stuck. So it's like a combination of reaction and impulse forces. So it's using the blades like an aircraft in one way, and it's also using the impact force of the water to move the external outside blades too. So it's using the water in 2 different clever and combined ways. There's been other turbines since, so the Pelton wheel basically works at much higher pressure heads, and but is not as efficient. And then the Kaplan turbine, we're going to go into these in a little bit of detail in a second. The Kaplan turbine basically uses the aerodynamic effect rather than any impact forces, so it moves very, very fast, but it can't handle a very high pressure differential. Obviously, if we needed to do that, we would have to start rotating the blades so that it didn't shear in any way, and then you would end up with a Francis turbine. Interesting fact that I thought I would share. I've done a little bit of research, and I found that the world's first ever hydroelectric project was actually used to power a single lamp in Northumberland in England in 1878. This is not that light bulb, because I don't think it would have produced this much power, but it's a light bulb. Okay, so just to dig in a little bit about the different kind of turbines. So the Kaplan basically is what we talked about just a second ago. So this is the lowest pressure head, and I've marked it up at the top there. So 0 to 60 meters, right? Anything more, and we're going to start to have too high pressure differentials, and the blades would start to be under huge kind of stress and then end up shearing. But if you think about using these in an opposite way, I mean, it's basically the same as a propeller design, right? So they can move very, very fast, and they can move a lot of water, and that's where they're good. So for very high speed flows, but low pressure. The total other end of the scale, so if you check out the pressure head at the top, that's 1.5 kilometers of water that this could have above it and not get destroyed. this is where these are good. But there's also a happy medium, right? So the first one, if I just flick back, this is like a reaction turbine. So it's using the pressure difference as the blades are moving through the water. So the water's moving the propellers with a pressure differential across each blade. These don't do that at all. So they're only using the impact force of the water. The nice thing about the Francis turbine, and I think why it's stuck around for so long, is because it uses both. So it uses the impact force and it uses the reaction force. So it has the pressure difference over all of the blades, and that also kind of sucks it around. And when we get to start looking at the model in a second, you'll see if we look at it from the top as well, there's also many kind of fins up there, all with aerodynamic shapes too. So there's like a double kind of layer where we're extracting a lot of energy from the water. Okay, so this is what we're going to look at, and this is the exact model actually. So just to talk you through it a little bit, on the left-hand side we have our inlet, and the water flows here and through the casing, and the casing diameter changes as it goes to keep the water at basically the same velocity all the way around, and a lot of it obviously gets sucked into the runner or impeller, you might know it as, and then it passes out through the draft tube. The interesting thing as well about the draft tube is that it has to expand in size, basically because we want to reduce the velocity as much as possible and raise the pressure. And just to take a little bit of a look inside too, so this gives you an idea of, you can see the flow would come like along the top and pass clockwise through the valve, through the structure. The bluish kind of vanes are static, relatively static. So that they're essentially the stator, but they can move on their axes. In our analysis, we haven't done that because we've gone with a fixed flow rate, but they would kind of change and move based on the flow speeds moving through the model. And that's important because we want to obviously have the most optimum energy extraction from the water. And that's where CFD can help too. So, initially there's no way that I know of anyway that we would know what kind of angle to have those blades positioned at. And you could do it through test, of course. But with CFD, we could optimize that before we built anything. And then obviously from there, the flow moves into the actual Francis turbine in the center. So the other thing I think that's useful to use CFD for is the design of the draft tube at the outlet. What we need to make sure we do is expand the fluid gradually without any recirculation. So anytime we have recirculation, we're basically using the energy of the water to do something that we don't need. We might also be accelerating it and causing cavitation, which then also is going to wear all of our components much faster. So this is it basically where we're going to get to. So the flow passes in at the left and you can see it spinning around the center. These trace lines are shaded by velocity, and you can see the scale on the right, so it goes from like 0 to 30 meters a second. And the interesting thing is this design is not too bad because the velocity is basically the same all the way around. So if I go back one slide actually, you can see on the left here the space where the water has available to move is much less than it has on the right, because a lot of the flow has already kind of gone through and out of the draft tube. But we need to make sure that that velocity stays fast, right? Because we want the loading to be pretty equal on the turbine and the bearings associated with it. Okay, so just a little bit about how to kind of get started, and then Darren's going to take over and jump straight into the platform and just show you how we would go through setting this kind of model up and how we can extract some results. And then I'll jump back again and we'll kind of talk through some more results in detail. So there's basically 3 steps to go through, and Darren will cover them in a second. But the first one is to import your CAD, right? So we're based on the cloud. Everything is in the cloud, and most of the engineers that I know of work on their desktops. So basically you need to get your CAD and upload it, which you can, directly into the SimScale interface. The second step is meshing. That's pretty well automated. So there's a totally automatic mesher, but you're also, if you have the knowledge, totally free to modify that and go to any kind of manual degree that you would like to. And then the third step obviously is design decisions. So once you start to get an idea of what's happening, where the flow's going, where you've got recirculation, where you might have cavitation, and obviously you don't want that, then you can start to optimize your design. And the setup process there is very straightforward. So you can easily just clone or duplicate a simulation and push new geometry to it. And the setup stays the same. So you haven't got to repeat that process again. And then obviously because we're cloud-based, you could run, I could say 100 or thousands. You can run as many different designs side by side as you want to, and they would all run in parallel. And then you can compare them again side by side to get an idea of which design was the best. So the last slide is just the boundary conditions. So this is kind of what we would do normally to produce a pump curve. So on the outlet we have a pressure, and on the inlet we have a flow rate. And we've assigned a few different flow rates from 8 to 16 cubic meters a second. This is quite a small model that we ran, by the way, with the fixed flow rate. And then what SimScale will give us is the pressure drop. And through that, we can easily create a pump curve, which is at the end, what we want, because we would like to know, ideally for the whole curve, where the point of efficiency is. And that's then where we operate our turbine. Okay, at this point, I'm going to hand over to Darren for a few minutes, and he's going to walk you through the platform.
Excellent. Thank you very much, John. Right. So firstly, what we want to do is we want to start with our geometry. And what we actually want is we just want the fluid domain. So that is, we want to extract only the fluid part from the external geometry that we would have designed. So if I just hide a few faces here, you can actually see the geometry of the structure inside, and hiding that one there. Once again, we can see the blades in there as well. So this is our fluid domain that we're actually going to simulate. And the first thing we'll want to do is to create a mesh. So we can move over and create a mesh directly by right-clicking on the geometry, or we can go onto meshes and mesh from a geometry there. What we really want to do in meshing is we want to make sure that we get enough resolution in the mesh to actually capture not only the physics, but we also want to capture the features of the geometry. So once again, hiding a few faces, what we actually want to do is make sure we've got enough mesh resolution around these blades. Just hide that one there. And similarly in the actual turbine itself. And this can be done by creating refinements. Now refinements can easily be created by just adding a refinement here. And we've got a few different types of refinements that we've used. So we've used a few feature refinements. So what that basically does is it takes all the edges and it refines upon those edges. We've got a region refinement. So basically anything within a certain region is actually refined to a set level that we've defined. And finally, we've got cell surface refinements. And in fact, this cell zone refinement actually creates the cell zone in which we're going to allocate the rotating zone to. And that's quite important in our setup today. So the output of this meshing process is actually a mesh that looks like this with two cell zones. We've got the rotating zone in here, which is where the turbine actually sits in, and that's going to be set at a certain radial velocity. And we've also got the rest of the fluid domain, which is our zone 0. And from here we can just go straight into setting up our simulation onto the boundaries of this mesh. So simply we can create a simulation by adding and choosing the flow type that we actually want to analyze. In this case it was incompressible, since we're dealing with water, and we selected a domain, either the initial design or the modified design. So what I'm showing you here is just the modified design. What we have to do is create a material. We can either do this by defining it explicitly, or we can just choose from a whole library of materials, and that's available in the SimScale platform. The boundary conditions that we actually require to set here is actually not too detailed. We've got an inlet boundary condition, which simply defines the flow rate, and we've got an outlet boundary condition, which because we're in incompressible, we can set to any value and the results will be the same. We've got a few advanced concepts that we have to use because we've got a rotating zone. We can create a rotating zone from one of these options where the MRF is the preferred type of rotating zone for steady state. And in here is where we define the axis of rotation, the center of rotation, and also the radial velocity. And finally, what we can actually do is we can explicitly tell it to return a certain results. For example, if we want to work out efficiency, we need to know the forces, the torque on the turbine, and we also need to know the pressure difference across the system. So forces and moments is actually applied here, and the center of rotation is applied at the center, the same as the MRF. And what this actually does is it takes a moment around that that position, and it returns the torque for us. And in surface data, we can set as an inlet and an outlet separately so that we can see whilst it's solving how well it's converging, and at the end we can actually define how much that pressure difference is. And what we've done is we've just asked it to return every 10 seconds. So whilst the simulation's running, you can actually monitor its convergence using the convergence plot. And we can also see the force plot and the area average plots whilst we're solving as well. And once we've actually created all of our runs by changing the flow rates, we can run all this in parallel, and then we actually want to analyze the results. And we can do that directly in our post-processor on the cloud by clicking on solution fields. I'm just going to hop over to another tab because that does take a few minutes to load there. So if you select on the solution fields, this is the sort of user interface that you're presented with, and you've got all of your filters here to be choosing from. And all I've done here is I've seeded basically particle tracers at the inlet and the outlet. That can simply be done by pressing the big plus on the particle tracers, and you can vary the parameters if you like. For example, the radius of the tubes, or indeed the actual coarseness of that seeding. Like so. And that just gives you a demonstration of how we can actually analyze the results within our turbine.
So a question for you, Darren.
Sure.
Why is that useful?
This is useful because we can actually look into detail on how the flow is moving around our geometry, how it's interacting with the blades. If it's correctly being guided around, which we can see actually it's being deflected by our stators here, and guided straight into the turbine blades, which we can see running straight up the middle. And then we can follow it all the way out of the duct, all the way to the outlet. And this helps us understand where recirculation zones may occur, where any efficiencies might occur. And we've got a whole host of other filters that we could use to actually further understand the flow. For example, we can apply cutting planes to actually analyze any turbulence properties, velocity magnitudes. We can also post-process further offline to actually get things like cavitation number, where we can determine where cavitation is actually likely to occur.
Okay, you're giving me thumbs like you're finished. Let me come back. Thanks, Darren. Okay, so I would say at this point, if you have any questions, then feel free to ask them about anything that we've talked about so far, anything that you've seen in the platform, anything you want to see in the platform, and we can either try and show them, as we go, or we can talk about them a little bit afterwards. Okay, so what I wanted to do is just kind of talk a little bit about the results, right? So Darren showed like a little bit about what you can see, but I thought let's dig into really getting some numbers and making it kind of useful in answering some design questions, and then get an understanding of how we can, or if we can, make the design any better. So going through like the beginning or from the inlet towards the outlet. So the inlet already starts to be kind of critical because, as you can see on the left, the cross-sectional diameter, or at least the cross-section, depending on the shape, will reduce. And what we're trying to do is accelerate the flow and get it to basically move all the way around the whole volume, and not kind of just disappear into the stator and the turbine at the very beginning. We can see that that is happening here. But again, you know, what we don't know, and what we could find out easily with SimScale is what would happen if we changed the diameter here, right? And how could we, would it improve our design or would it make it worse? So we could make a quick geometry change in CAD, upload it again to the SimScale platform, utilize the same simulation setups, and then compare the results again side by side. Taking a look on a slice through the top, so here we're showing velocity, and it's shaded, the cut plane that you can see is shaded by velocity. So the blue is basically zero velocity, and that's pretty much where we've got recirculation and potential cavitation, and then up to the red, basically where we've got the highest velocities. And the goal really is to have all of this area kind of coming all the way around the outside, to at least have the same volume flow rate. What we can see with this design, and it's not great, is especially take a look at the stator at the bottom down here. We can see like large regions of blue basically. So the flow is coming in here and it's basically going around in between the two groups of stator blades, and it's not kind of passing into the middle and getting into the turbine, which is where we need it because that's where we can extract the energy. So already, you know, we could think, okay, there's some changes we can make there. And would they make a difference? And we can see the same up here at the top. If we take a closer look, it's kind of a little bit easier to see, I think. So this is just a kind of zoomed in version of that, basically. And you can see, if you take a look at that arrow there, I mean, we could show more, right? But the flow is going backwards. So we've actually got really recirculation there. And the recirculation is expending energy, and that energy isn't being extracted and then being used to power homes. Okay, so that was, we'll get onto the design change in a second, but that was like one of the design changes that we thought we would try to make, is to change the angles of these stator blades to see if it made any difference. The other important thing, I think, is longevity and the lifetime of our design. And here basically we're looking at two things. This is a single blade and looking at the front and the rear. So on the left we have the front of the blade, and on the rear we have the back, right? So this is the back, it's like a plane wing essentially, but the right-hand side, which is the rear of the blade, is the top of the wing. So that's basically where the flow has to go the fastest. And we have a lower pressure, and that sucks the blade around in a circular motion. But what we also need to be really cautious of is to not drive the flow too fast, because then we might end up with cavitation. And that means if we get to below the vapor pressure of the fluid, then we basically have micro bubbles of air, and when those micro bubbles burst, they're going to basically, they cause a huge amount of power and energy and release it, and it all basically explodes on the surface, and that will start to kind of wear away the surface of the metal, and then we have erosion. The other thing I think that we could improve from this design, and we will in a second, is the flow through the draft tube. So if you take a look at these two areas, on the left we're looking at the pressure, and you can see the pressure dropping from low to high, which is what it should be doing on the way out of the draft tube. So as it's slowing down, the pressure is going to increase. We would like that to be a nice gradual change. If we have any kind of very quick changes, then again we're probably wasting energy. Or on the right, this is even worse. You can see that the flow basically tends to the top and it recirculates at the bottom. And recirculation, again, isn't like a great thing to have in any of these kind of designs. And here's a nice way of visualizing that. So this is what Darren showed before, but just with a few more traces flowing through the model. You can see, I mean, I've highlighted one region of recirculation, but there's many in this design. And if we can reduce those and at least move them way downstream, then again, we're going to optimize our design, and we're going to improve the efficiency, and we're going to be able to extract more energy from the flow. You can see really a lot of questions, by the way, and we'll try to talk to those at the end. I think Darren's going to answer all of them, right, Darren?
Yeah.
Right, Darren?
Absolutely.
Good. Okay, so what we're going to do is just do a quick design comparison. So basically, we've highlighted two areas of interest, I think, or two areas where we had questions, from being able to see inside the product using CFD. So one is the angle of the stator blades. Can we reduce the recirculation on the tops of those blades? And will that improve our efficiency? Will we extract more energy from the water? And the second is the design of the draft tube, which wasn't great. So we've tried to change the draft tube here. And if I show you as well, we also changed the stator angles. So basically on the left is where we started. And on the right, if you take a look at, say, this very top one, we've given them a sharper angle. Actually, what I think in hindsight is that they shouldn't even have all the same angle. Depends on how you look at it, right? So I think we could design the volute differently to control the velocity of the speed of the flow differently. Or we could not have all of these with the same angle because the velocity isn't the same all the way around. It kind of depends on how you look at it. So just to remind you, right, this is what we're trying to fix, this recirculation here, for example. Okay, so these are the results. So on the left we have our initial design, and on the right we have our modified design. My personal opinion is we made it worse, right? So we thought we'd make it better, but we didn't. But that doesn't matter. We learned something, and we learned that actually, so take a look up here and down here, for example, we learned that changing the angles of these blades can actually introduce more recirculation. So the question now is, do we reduce them a bit less? Do we change the angle of the ones on the right and leave these the same? And that's what we can do now with SimScale. So we can make all of these changes in CAD, push it all to the platform, reuse our simulation setup as a template, and just set them all up and let them all run. And they would all run in parallel. So the time it takes for one to run, you could have run 100, and then you can start to compare results. And then, we can, without even going into the results, we can basically use like probe points or monitor points in the model to get an idea of where we had the most efficient design. What we did improve, I think, was the flow through the draft tube. So on the left, we basically have quite a steep change from the high pressure to the low, or the low pressure to the high, apologies. And on the right, you can see it's a little bit more like a rainbow. We've really kind of drawn out the pressure increase, and that is what we want. And again, we can see here, so on the left, there's a lot of recirculation, and it's actually pretty messy, the flow. Basically, the problem is the angle is too sharp for the speed of the flow. So you can see that actually most of the flow shoots through and is passing along the top, which is why it is green. And the flow, which is blue at the bottom, is nearly on the right here, right? Like 0 to 2 maybe. And that's basically either going backwards or being is chaotic flow, I would say. It's not really kind of exiting in a smooth way, which is what we would prefer. On the right, it's better, but actually you can see what shape we should have, right? So if you follow the line of where most of the flow is going, that is the shape the draft tube should have at the end. Okay, so the interesting thing I think for me is that we took a design and we have made it better despite making one thing worse. So we've increased the efficiency, so we would get more energy from the water. And you can see on the right, what that really means. The interesting thing is if we spent more time and improved or really focused on either the design of the volute to direct the flow better through the stator, or we started really messing around with the stator angles and design, we could really improve this much further. But if you think about it in reality, how would you know that, and how would you make it better? You couldn't really manufacture these, right, and batch test them and prototype them. Of course, you could change some things, and on the next installation, you get an idea, but that doesn't make sense, right? So to do it this way, basically in a day or two, and to optimize the design, that to me at least is like the power of SimScale and the power of the cloud, and that's where we should be utilizing CFD. So just to quickly sum up, and then we'll attack some of your questions, which by the way has passed a page size. We know that we've made the design better. We know that we could make it better still. So I think the draft tube is better. The stator design is not. But overall, we've increased the efficiency, so it's good. I think we know what is good is that we know why we've made the design worse in certain areas and what to do about it. And we could only do that, right, by seeing inside and getting an idea of what exactly is happening. So now we know it's very clear what we need to do next. The draft tube should follow more the design of the flow. The stator angles that we changed from the original to the modified was too big a change. So we should try something in between the two. So that would at least be my next starting point, right? So go from one design to the other and cut that change in half and then compare again and see where we are. And then we can start to really hone in on the optimal design. Okay. So, questions and answers. Thank you for listening, first of all. That was 40 minutes of Darren and I talking, which is a long time to listen to my voice, I know. So thanks for listening. Let's try and talk to some of your questions.
So I think the first question we had was to provide a brief about the MRF method used in the simulation. So I think that's best actually if we go straight back to the platform. So navigating to the MRF, what the MRF actually does is it doesn't rotate in itself, but it actually applies the rotational forces to the fluid within that region. So this kind of simulates the rotation, but without actually rotating it. And this is ideal for steady-state simulations. The next question was, what if one has to find the rotational speed due to fluid flow? So what we can actually do is we can actually apply a vorticity field. We can do that straight here in the platform. Just by coming to result control, field calculations, and we can add vorticity right here. So that's actually going to give us an angular velocity, but we could also do many other manual calculations with the calculator fields as well. So
I think I can probably speak to that one. So the question was, can the flow be visualized as a video output? So yes, you can animate the traces that we have here. And yes, because we saved every 10 seconds, you can animate the model. And yes, you can see it rotate. Yeah, that answers the question.
I think so. Additionally, I think you can also bring it into the offline post-processor and do some amazing video outputs as well. So all of the file types that we have here at Simulation, SimScale, is supported in PowerView as well.
I think that's an important point, actually. So basically, I think a nice thing to know is, yes, everything's hosted on the cloud, and yes, everything's stored on the cloud. Yes, everything's kept on the cloud. But if you want to keep something locally, you can, right? So at any point, if you go to the results, you can download them. So here, you can download the results, and then they're yours, right? So, and you can delete them from the cloud if you want to. So you're in full control, and you're really the owner. And I would say you can also, like Darren said, you can move it into any other kind of product and then start to view the results in different ways if you choose to. And we haven't put this model online just yet. We will, of course. I think once we email out the webinar recording, and we can basically send, I'm sure we will, in fact, send the link to this project with it.
Yeah.
I wanted to talk to this one, actually. Will recirculation result in cavitation? Possibly, but it's not necessarily. I guess like the bigger cause of cavitation is lower pressure. Recirculation is normally where the flow is a lot slower. The recirculation more is wasting energy at the end, so where the water's burning up energy and it's not giving it to us, in the form of rotation of the rotor. The cavitation is more likely to occur, I guess, where you've got the very high flow and the very, very low pressure. So if we drop below the vapor pressure and then the water suddenly vaporizes into air, that's where we're going to start seeing cavitation.
In addition, one of our previous webinars, pump design, we also visualized a cavitation number there. So you could also check that out to see how we did it. Can we use the incompressible lattice-Boltzmann method for this simulation? At the moment, no. We don't support rotating zones, but that's not to say it won't change in the near future.
I'd also say, the LVM code, I mean, we see, this is a little side topic, but we're seeing a lot of growth in the AEC market, and that's where our solver, well, actually most solvers, isn't so great because you need to run very long transient analyses. And that's why we've moved towards LBM for those. So the very long kind of transient studies on massive city models with hundreds of million elements. That's where LBM is really super useful.
Yeah. But
for this, honestly, it didn't take that long to run. And you can see at the top right, it took 180 minutes to get from when we hit go to the end. So that's not so bad, I would say. And you could run lots of different analyses all side by side, right? So within 3 hours, you could have pump curves for hundreds of different designs at the end.
How will the efficiency be affected if we increase the surface area of the blades instead of changing the angle? So we've really changing the surface area was likely to increase the lift of the blades, so that would increase the shaft power, so our efficiency would actually increase. But in the end of the day, we've got to put it in CFD and see if it's worth changing the area of opposed to changing the angles and things like that. You don't know which parameters are going to make the most effect, and that's where you could set up a design study.
Okay, so somebody's just written answer me, and I feel like we should. So I think that refers to this question: how do we identify issues in the design? Just by looking at the results. And I'd say it wasn't so hard, right? So if we go back, let me go back a little way to say here. So basically what we wanted to avoid is recirculation. And if you take a look, say here, I think it's a really nice example. Like there's many regions here where the flow is recirculating quite heavily. And also if you say take a look at where the flow is entering the turbine in the middle, the speeds here should all be equal, right? Because we don't want to side load our rotor. We don't want to adversely wear the bearings, and everything basically in a circular machine needs to be symmetrical and balanced. And the flow here simply isn't balanced. So that's really our starting point. And I would say the same for the draft tube. So if I find the draft tube, again, you know, we can see there's recirculation here, and you can see, I think, a lot of the flow kind of shoots up to the top and past the low flow that we have here. And that is kind of how we would start to decide on how to optimize the design. I think we've answered most of the questions now. What I'd say we'll do is, well, if there's any that we haven't, we can mail you directly. I mean, honestly, there's a list of questions, but I think most are repeats of others. So at this point, I would say we'll probably wrap up. And really just thank you for your time. We will answer the other questions that we see there, because some of them I think we should, and they're not quite the same, but not applicable to everybody. So we will reply to those results. But simply, thanks, I would say. Thanks for joining. I hope you enjoyed the webinar and you learned something. If you would like to start using SimScale, you can. You can sign up for a free account. That gives you core hours, so you can start using it immediately. And you can reach Darren and I as well if you start using the chat function. So just hit the little the speech bubble on the right hand side, and we'll be online, as well as all of the other engineers to help you as you get up and running. So thanks for your time.
Yep, thank you.
Have a nice afternoon.